What's up guys, it's me, Sir Ernest, and today we're going to solve problem 8.11b of Fowles and Cassiday 7th edition. The problem reads, a circular loop of radius A swings as a physical pendulum about a point on the circumference. Find the period of oscillation for small amplitude if the axis of rotation is in the plane of the loop. So in problem 8.11a, our circular loop is rotating about the z-axis. So the swing is in this direction parallel to your screen. Now in this case, the axis of rotation will now become along the x-axis. So that with respect to the x-axis, this circular loop will swing back and forth relative to this plane. So if we're going to change the perspective, the problem would look something like this. So this is your z-axis, this is your y-axis, and out of the page is your x-axis. So therefore, your loop would look something like this, and this will swing in this direction. So that means we need to find first the moment of inertia of the circular loop about an axis passing through the center along the plane of the loop. If we're going to write that, it would look something like this. So this is our loop, and then the axis of rotation is about the y-axis. This is our line element dl, and by polar coordinate system, this is equal to a d theta, where d theta is this angle, and theta is measured with respect to the y-axis. If the y-axis is our axis of rotation, therefore the distance of this mass element would be r. R, theta, and A is related by this relationship, R equals A sine theta. We know for a fact that the density is uniform and it is equal to the mass divided by the circumference of this loop, and this is 2 pi a. So therefore, the moment of inertia about the y-axis is calculated as integral of r squared dm, and this is equal to integral of a squared sine squared theta times rho times dl, where dl is a d theta. So as you will notice here that the integration will happen along the coordinate theta, and that will vary from 0 to 2 pi. So we write it here, 0 to 2 pi. And doing the integration, the moment of inertia about the y-axis would be equal to rho e cubed pi. Using the expression for the density, this is now equal to 1/2 ma squared, which is different from the moment of inertia of a circular loop about an axis passing through the center, but the axis is perpendicular to the plane of the loop. This moment of inertia, Iy, can now be used to calculate the moment of inertia for our system. So therefore, by parallel axis theorem, the moment of inertia will now be equal to 1/2 ma squared plus ma squared, where a is the distance between the axis from the center of mass. Simplifying this, we now have I equals 3/2 ma squared. So therefore, the period of this object that rotates about an axis along the plane of the loop passing to the circumference is equal to 2 pi times the square root of 3/2 ma squared divided by mga. Simplifying this, we have 2 pi times the square root of 3a over 2. That's it. This is the period of oscillation we are looking for. And if we're going to compare this to our previous result, this is less than the period where the object is rotated normal to the plane of the loop. This is our result from our previous example, 8.11a. So that's it. That's the solution to problem 8.11b of Fowles and Cassiday 7th edition. I hope you learned something today. Thank you guys for watching, and I'll see you guys in the next video. Bye-bye.